Hello everyone, my name is Dr. Jyoti Tiwari and I'm a postdoctoral fellow in the Department of Earth Sciences at IIT Bombay, working under the supervision of Professor Soumyajit Mukherjee. Today I'll be presenting our collaborative study on a Chamoli disaster of 7th February 2021. Our goal is to understand what happened in an Himalayan avalanche and how real-time seismic monitoring can prevent some lives. The topic of my talk today is potential seismic precursors and surficial dynamics of a deadly Himalayan disaster and early warning approach. The Himalayan glaciers are rapidly retreating due to increase in glacier melt and climate changes. The retreating of these glaciers and associated melt with unstable slopes and steep topography are prone to landslides that lead to development of lakes. These can be triggered by some intense monsoon or some seismic activity leading to a disaster in a Himalayan terrain. The article was published in Scientific Report in 2022 and was co-authored by Dr. Anil Tiwari, Dr. Kalachan Sai, Dr. Amit Kumar, Dr. Ajay Paul, Dr. Naresh Kumar, Dr. Chinmay Haldar, Dr. Sushil Kumar and Dr. Chavi Pandey. Let's take a closer look at what happened. On 7th February 2021, a catastrophic rock ice avalanche struck the Ronthi catchment in Chamoli district of Uttarakhand. It caused a devastating flash floods in Rishi Ganga and Dhauli Ganga valleys, destroying infrastructures including 2 hydropower projects and lives of almost more than 100 people. The event reminded us how closely geological processes and climate interactions are linked in the Himalaya. Our focus is to understand what triggered this avalanche and how seismic monitoring can prevent some lives. This is the Ronthi catchment, the source of the avalanche. This is from where the wedge failure occurred. This red zone is marking the area affected by this avalanche. This is the 35-degree slope plane for the avalanche that occurred. The affected region was in the proximity of main central thrust in the Himalaya. Before proceeding further, the seismic signatures are not only just a characteristic for an earthquake, but they can tell us about different sources. Like this is a seismic signal for a debris flow. This is for a distant earthquake. This is a tectonic earthquake. This is a rockfall, and these are the glacier gliding noises. This means that not just earthquake, but other sources can also be known from these seismic parameters. Now, let's know about the geology of the affected area. The region comprises of kyanite schist, pegmatite gneiss and quartzites and a steep slope of approximately 35 degrees. There were some pre-existing fractures that influenced this detachment. Satellite images showed gradual cracking in the area from as early as 2015. This tells us that the region was structurally unstable for years. Then, about 2.5 hours prior to the avalanche, Wadia Institute of Himalayan Geology's seismic stations recorded continuous tremors. These were not felt by human but was recorded in the machines. These tremors indicate a nucleation phase, that is, a slow buildup that leads to the failure. With that background in mind, let's move on to what happened and how to prevent it. Wadia Institute of Himalayan Geology, Dehradun, has deployed broadband stations in various parts of the Himalaya. For this particular study, we have used the nearest station to the source zone, that is Tapovan Station, Garud Ganga Station and Adibadri Station. Using waveform cross correlation, we identified seismic signatures with similar sources and characteristics across stations from Tapovan, Garud Ganga and Adibadri. This strongly supports that the signal originated from crack growth in the wedge that failed. Continuous high-frequency tremors were active before the actual failure. The seismic signature from this avalanche was recorded in Tapovan Station and Garud Ganga Station on 6th of February, that is a day prior to the main avalanche. This is approximately 12 km from the main source zone and Garud Ganga is approximately 20 km from the source zone. Now, to know what is the source for both of these data? Is it coming from the same source or is it a different source? So, to know the actual source zone, we did a cross correlation and got that both of these tremors are from a single source. Since Tapovan was the first station to record the data consistently, it was known that the source has to be nearby this Tapovan region. So we concluded that it has to be somewhere close to this Tapovan station. This is the log amplitude and frequency map. This shows that the data fits perfectly in this log amplitude. You can also see a P to S wave that is basically concentrated with earthquake data, but here we have found P and S wave because prior to the main event, minor cracks have initiated at a depth of approximately 200 meter that automatically makes it a subsurfacial event. Also, there was spike in the tremors before the main detachment, that is at this point that the main avalanche hit. But you can see prior to this, we have seen a huge spike throughout the data. And as soon as it is released, it has relaxed and fallen down to its initial value. Let me guide you through the disaster timeline reconstructed with high precision seismic data and field validation. This profile shows the path of the avalanche from high elevation to downstream valley. The avalanche started with a high velocity of 55 meters per second, which is extremely fast. As it moved downslope, the material fragmented, get heated, and fluidized to make it a slurry and cause the devastation throughout. Once the avalanche was triggered, the movement of the material followed this path. Let us look at how this flow behaved and what it impacted along its way. This is the point of the cliff top, and this is the point where the main detachment occurred. And from this point to this point, it hardly took 15 to 17 minutes for all the disaster to occur. There was enough time to save people if it had been an early warning system. At this point, the initial crack started, and as soon as it hit this point, this is the point where Ronthi and Rishiganga stream confluenced. Then it hit the Rishiganga dam and moved on to hit the Rani bridge and broke the village throughout. Then it moved towards the confluence of Rishiganga and Dhauliganga, and the velocity decreased from 55 meter per second to 27 meter per second. Then later, as it moved and hit the Tapovan station, that is at this point, the velocity decreased to 9 meter per second, destroying this NTPC dam. Field surveys were conducted post-event. Observations confirmed massive boulder deposition, dammed lakes, and structural observations. The steep relief of more than 2000 meters and terrain morphology specially accelerated the avalanche. The high-speed debris flow hit major structures like hydropower projects and bridges. The impact speed dropped to 13 meter per second and later to 9 meter per second downstream. The energy of the flow was enough to breach the dams, barriers, and even dam gates that led to the amplified disaster. This is the point of avalanche release zone. These dotted line represents the path of the rock ice avalanche material along the Ronthi stream. This is the Ronthi stream, and this white line denotes the effect of the debris. It can be seen that it reached to a highest point at many places. This is the confluence between Rishiganga and Ronthi stream. This is the place where Rishiganga hydropower project was completely damaged. Then moving on to this Rani village bridge, it was approximately more than 150 meter above the river's bed, and it was completely damaged by this slurry. So you can feel how much pressure the water has with itself. This is the schematic diagram showing different velocity speed. From A to B, it was 55 meter per second. Moving from B to C, it decreased to 27 meter per second. From C to D, it reduced to 13 meter per second. And later from D to E, it came down to 9 meter per second downstreams. This figure shows the confluence between Rishiganga and Dhauliganga Valley. It is at this point where it hit a highest of 150 meter and the water moved upstream in Dhauliganga river, thus reducing its speed and reducing the devastation throughout. This shows the slurry deposited material at the Tapovan Dam village. Two major hydropower projects of Rishiganga and Tapovan were destroyed. High seismic amplitude spikes aligned precisely with the video confirmed timing of infrastructure damage. These correlations validate the use of seismic signature for real-time impact detection. In summary, the disaster was a result of geological instability and climate triggers. The seismic network detected early warning signs that preceded the avalanche. Integrating seismic, satellite, and field data can give us a powerful tool for such disaster. This disaster showed that seismic station can detect signs of failures prior to any event. Signals we saw ranged from 10 to 35 Hz. that are particular for shallow, near surface rockfalls and avalanches. So, what we conclude from this entire investigation is that a study underscores how real time seismic monitoring, especially high frequency precursory tremors, can be leveraged to detect early signs of slope instability. With monitoring system already in place, enhancing network density and coupling it with early warning system can drastically reduce disaster risk in the Himalaya. To wrap up, this event showed us that nature can provide us subtle warnings about a disaster before it happens. However, if we listen carefully through seismic monitoring, we can potentially save lives. We thank Wadia Institute of Himalayan Geology, Dehradun, Department of Science and Technology, and Ministry of Earth Science, New Delhi. Thank you so much for your time and patience. Please feel free to contact us via email ID for further discussions. Thank you.